Our next talk will be by Fabian. He's a physicist from Münster and works as a software lead at Pixel Photonics, where he had the luxury of introducing Rust for most of the software stack, and he's going to tell us all about it. So give a great hand to Fabian.
Yeah, thanks a lot for the introduction, for having me here. So as was already mentioned, my name is Fabian, and I'm actually a physicist by training, and I work for a small startup called Pixel Photonics. This is actually a spin-off from Münster University in Germany, which is not so far from here. And what we do is we develop and build single-photon detectors, mostly for scientific applications, but also for stuff like quantum computers or quantum technologies. And we use a lot of Rust in our product, and this is what this talk will be about. But before I get to the Rust parts, I guess you deserve a slightly better explanation of what our product actually is and what it's being used for. So I'll give it a quick shot. So first, of course, you may ask what actually is a photon, and essentially, that's probably a question to fill in an entire lecture series on quantum optics. But for the purpose of this talk, you can just think of a photon essentially as the smallest amount of light that you can have. Of course, you can have no light at all, but then the smallest amount of light that you can have is a single photon. You cannot have anything in between. And to measure such a single photon is actually quite difficult because the energy of a single photon is just extremely small. So just to put, it's difficult to put that in relation to anything, but to frame it in a way that may look a little bit familiar is if you run this Blinky example on your Arduino or RP2040 or whatever, and you make this rather dim indicator LED blink, then already this small LED emits something like 10 to the power of 16 photons per second. And we only want to measure a tiny fraction of that, right? So we want to measure a single photon, so essentially the 1 over this number in terms of energy. And as you can imagine, that's quite challenging. So it's difficult, but it also has some quite useful applications because these photons have very interesting properties and very nice applications. So there's, for instance, of course, the quantum technology, so quantum computing, which is quite trending still. There's quantum communication. But then there's also a range of more traditional applications, such as LiDAR, where, for instance, you can benefit from detecting single photons, or also microscopy, which has applications in the life sciences, obviously, where you might want to actually see or detect single photons, or if you don't work with the quantum stuff, just very low light amounts. We actually develop and build so-called waveguide integrated superconducting nanowire single photon detectors, in short SNSPDs. And what that means is probably, I won't go into too much detail about what exactly that entails. But just this term SNSPD might occur a few times over this talk, so you should be, you should recognize it. And if you're interested in the deeper aspects of this technology, just come talk to me afterwards. And also, I think as Rustaceans, you're quite used to bulky acronyms, so I think nobody should be put off too much by this. This technology actually works quite surprisingly well, if you want. So we can actually resolve and measure single photons with an efficiency of more than 80%, with little to no noise, so almost no dark counts. So we get an extremely good signal-to-noise ratio, and also the timing accuracy is extremely good. So we can measure them with a timing accuracy of a few picoseconds, which it's just an incredibly short amount of time. We do this, we fabricate these sensors in-house, and all of the optical elements needed for that, together with our sensors, we put on these silicon chips. So that's more or less what it looks like. And this is similar to how integrated electronic circuits allow for miniaturization of electronics. And we do the same for optics. So we put a bunch of optical elements such as beam splitters and waveguides and filters on this chip together with these single photon detectors. So that's super nice. And with this also gives us a lot of scalability. So we can put literally hundreds of these detectors on a single chip. We call them pixels, hence the name. But of course, there's a catch. Because for all of that to work, this chip actually needs to be operated at cold temperature, so it needs to be cooled. And by cold, in this case, I mean very, very cold, because actually you need to run it at 2 degrees over the absolute 0 point, which is not super trivial to do. So in the end, a sensor that our customer can use doesn't just look like this, or once we package it and put some electronic and optical connections to it, it also doesn't necessarily only look like this. But actually, it's a big instrument that you can put on your, on your lab table or in your rack, and that contains a lot of secondary control electronics or control equipment to control the electronics and the cooling environment. So as you can imagine, someone using our sensor doesn't really want to deal with all the pumps, the vacuum system, the valve, and so on, and all the low-level electronics to drive that. So for that, we need a lot of automation and software in order to provide a turnkey solution for the customer or the scientist working in the lab. And now we're finally getting to the rusty part of the talk, because essentially all of the software running in this machine, or the custom software at least, is written in Rust. So that's rather nice, I think. And since this is a scientific instrument, but as I also already mentioned, we also touch a lot of aspects from the industrial automation part, because we drive, vacuum systems, pumps, valves, and so on. But I'll focus more on the scientific instrument part in this talk. And of course, this raises the question: why did we choose, or why would you want to choose Rust in such a scenario? And while preparing this talk, when I showed the slide to someone, I was told that having this answering this question at this conference is a little bit like preaching to the choir. And of course that's right, and I think I don't need to convince anyone of Rust here. But then again, this is probably one of the most recurring themes between the talks in this conference, at least judging from the talks yesterday. So I guess answering that question, I'm in very good company here. And it's also interesting, secondly, how wide the spectrum of arguments that we heard was yesterday. So, and I found a common theme among them was that, okay, the safety aspect, which Rust is most famous for, is very nice to have, but actually it's this list of other features that sold us to Rust. And for our use case, I really share the sentiment a lot. Of course, the safety aspect is nice. It prevents a bunch of errors that you otherwise have from other code bases. But I think the even stronger argument really is the developer experience as a whole. And of course, the safety is a part of this developer experience, because this, compile it once, or once it compiles, then it works. This experience you don't really know when you come from Python or C++, right? This is and also this plays a major role in the developer experience for Rust. But then, of course, there's other points also in this category, some of which we'll touch in this talk. Just to mention a few, it's the easy package management, the serialization, the ecosystem, basically with SERDI. You have excellent support for this, code generation support, macros, and so on. And then finally, if you want to also target embedded platforms, such as microcontrollers, there's not that many alternatives available, right? And I guess none if you actually want to also have a nice async environment, or a modern and nice async environment. So these are the most, these are the arguments that sold us to Rust. In the end, our system looks something like this. So we have a main control unit somewhere in our system, and as well as the electronics that actually drive the detectors themselves. We have some electronics driving the cryogenics and the vacuum systems, and then we also have some other subsystems. Sometimes we include lasers in there or other equipment. And we develop those, they are separate from the actual main control unit, both in hardware and in software, because they are developed more or less independently from the whole system. So our electrical engineers build small boxes, PCBs that contain, for instance, the control or the driver electronics for the detectors, and they need to be tested separately from the main device and then integrated into our device in the end. So these all run microcontrollers. In our case, we use the STMs, and we run also Rust on them. So all of this is basically running in Rust. On the other hand, we want to serve an interface that the user can connect to. So first of all, of course, the graphical user interface is nice, but also we need to have some interface for programming our instrument, so an API. And also then in the end, we need technical access for field technicians for doing field service and such. So not all of this is in Rust. In our case, the UI, for instance, is written in TypeScript, and scientists love Python, so we offer a Python API. But everything running in our system is actually written in Rust. And we also utilize Rust to generate a lot of the code that produces the API, so the Python libraries, and a lot of the TypeScript code is actually generated by Rust. So looking at the design goal of this diagram, you have a lot of communication between subsystems or between the user interface or the API, and a lot of which happens asynchronously. So you wait for data points from a measurement and so on. And so to me, this really screams for an async solution, because a lot of these points are actually kind of poster child examples of where you might employ an asynchronous solution. So for the main control unit, the platform that we use is a system on a module. This you might know this from the Raspberry Pi compute modules, for instance, but there's also other vendors offering these like Toradex or others. And the idea here is that you essentially put all the complex stuff like connecting the CPU, the USB controllers, Ethernet controllers they are already taken care of, and you just, as a user, you just build your custom PCB where you plug this into. Then you lead out the electrical connections or the connectors that you need for your use case exactly, and that's much easier than building a whole, this whole board by yourself. So we run this kind of thing. You can run a full-fledged operating system on this. And of course, since we're at a Rust conference, we all care about efficiency and only using the resources that we need. So you might argue that for most of these things, just for driving a few valves or pumps and so on, of course this thing is a complete overkill, and of course that's true. So the compute power that we get with these modules typically is much more than what we would actually need. But of course, you have to keep in mind that we are actually in an industry where the instruments cost tens or hundreds of thousands of euros. So the cost for the compute part, for just the compute part, and also the energy consumption really is not an argument here. Also, we don't sell millions of these devices, but we sell a handful of them per year. So for us, the much stronger argument is, of course, the ease of development. And it makes your life a lot easier for providing things like a graphical user interface or logging or connectivity and stuff if you have a full stack OS running on your device. And also with this, by the way, we're in good company because these days many bigger lab devices actually contain essentially full workstation computers with all the upsides and downsides that they bring with them. So in our case, we didn't want to have our users greeted by blue screens. So we use Linux, and we actually use Yocto to build a custom Linux system for our device. For those of you that don't know Yocto, it's essentially a build system which you can use to configure a Linux distribution exactly to your needs. And this is, of course, very nice for the embedded use case. And once you have this this Linux running on an ARM machine, is very trivial to run Rust on there because you can just cross-compile. The cross-compile story in Rust is very good. You have static binaries and so on. So that's actually relatively easy, but you actually might want to go a step further and integrate this Rust compilation step into your operating or firmware build process. And it turns out that Rust does actually have nice support with Yocto. So there's this meta Rust and the meta Rust bin packages that you can use for that. And then in the end, a recipe looks somewhat like this. So you inherit from the, so this is the Yocto file essentially. So you inherit from this cargo bin class, specify some metadata and the sources where they come from, provide maybe some environment during the compilation step, but cargo doesn't really need a lot of environment being set. And that's basically it. And then you end up with this binary sitting in your user bin directory in the firmware that you have in the end, right? So this is essentially how we include our Rust code or how we deploy our Rust binaries in the firmware that runs on the device. Now let's turn to the interface between the user and our device. So the left part of this slide essentially. And if you look at a typical lab or scientific instrument, the backside, so this is not our device, this is a source meter unit from Keysight. It might look like this, and you might find a lot of familiar connections and maybe some unfamiliar ones. So the first one that maybe you may notice is this bulky right connector here. This is actually a GPIB port, which is a very common port for scientific instruments. It's very old, it's from the 70s, but essentially every lab instrument these days still implements it, except for some newer and bigger ones, of course, don't. But from the big vendors, they typically still include this GPIB port. It's essentially a serial communication port with relatively slow data rates. Then you often find USB ports. And actually in USB, you have these device classes, and there's actually like human interface devices, for instance. And there's actually a device class just for scientific instruments. It's called the USB TMC, so test and measurement class. And this is nice because it allows you to have a plug-and-play solution. You don't need any custom drivers. You just plug this into your PC, and if you have a modern operating system, then it recognizes this as a measurement instrument, and you can almost immediately start talking to it. And finally, there's Ethernet. using some kind of TCP connections. Of course, Ethernet is ubiquitous, it's always available. Here the device discovery is not as straightforward as with USB, but you can configure a static IP that you give to the customer, or you can use something like DHCP to integrate into the lab network. And also you can announce some services using MDNS or similar solutions. In our case, with a similar argument than before, we settled for Ethernet because so we don't implement these yet. We only have an Ethernet connection in our case. And the reason for that is because, again, it's much simpler. I mean, how many people in this room have actually written a USB device handler? Probably not so many. Okay, so I see a few hands. And how many have actually written a TCP endpoint at some points in their life, right? That's probably everyone in this room. In that case, of course, Ethernet is just has a very low barrier of entry and makes things a lot easier for us. But also, it allows us to serve additional stuff over this Ethernet port, like a graphical user interface. So we actually run this user interface that I showed you as a web app, which is actually only served from our device and is served over this Ethernet port. Finally, for us, it makes a lot of sense because in the long run, we envision our product also to be integrated into data centers at some point, and there, obviously, Ethernet is also the port that you want to use. Now, for the software interface, today you would probably use something like a REST API or something, but there's actually a standard for scientific instruments. It's called SCPI, and this is actually from a time where I think HTTP and JSON both didn't exist yet, so this is quite old, but it's still very ubiquitous in lab instruments. A lot of them support this, and it's essentially consists of ASCII commands and queries, and they are ordered in such a hierarchical tree. So for our example, you have some top-level commands which are standardized, like giving your identification or reset the device, but then you also have this hierarchy, the structure, which maps nicely to the subsystems that we have in our case. So for instance, for the cryogenics, you may have a subsystem which is the valve or the pressure reading, the temperature sensors. And then you have multiple instances of the SNSPDs, of the detectors, which also expose different API endpoints. The support for this in the in labs is very good. You can call this from Python. There's a library called PyVisa, which is so you see these kind of scripts a lot. So essentially, you just open the socket, list the instruments that are available, and then you write the string to the instrument and get an answer back. So this is nice, and we do want to offer this as kind of a standard compliant baseline, but we also would like to have some more features for our instrument. For instance, in the Python interface, it would be nice to make use of things like type hints or doc strings and stuff like this. And it's not uncommon to have like wrapper libraries in Python that actually wrap over these SCPI methods, similar as to you have it often for REST APIs. You often also have some wrapper libraries, so you don't have to specify the REST endpoints manually. And yeah, so with this, the code actually looks then a lot nicer because we can actually, we offer the library to the customer, which then can just call methods or properties on our class. And they actually also get error messages if they have a typo or something. So this improves the user experience a lot. And also you get a nice documentation with it that you can just send the customer because you just include a lot of doc strings in this library. And finally, for something like the graphical user interface, it would be also nice to have some kind of publish-subscribe mechanism so that you don't have to pull a sensor value once a second, like the temperature, but you actually get an automatic notification for updates. So this is also, of course, a problem that occurs in many aspects of the, also in other industries, but for us, this was also a very important point. And so with that in mind, we also implemented WebSocket API. Since we have a web interface that serves this, we use the WebSocket connection to actually broadcast real-time events. And this also has some more benefits because it allows us for better error handling. So the error handling story in SCPI is not really good. And also it allows for these real-time subscriptions and also for better support for structured data. You can just submit some JSON, which is easy to process in the front end. So essentially, in summary, the interfaces that we serve on our device to the customer is this SCPI port, or this SCPI service over a raw socket. And then also the WebSocket-based API, which is a little bit more advanced. in terms of functionality that it provides, and a user interface, which is just a normal web app, which is served from our device so that the user doesn't have to install anything. They just enter the address of the device into the browser and see the user interface. And of course, this is now we have multiple APIs. I mean, this just uses the WebSocket API internally, but at least we still have these two APIs. And here you have some double effort because now you have multiple APIs essentially leading to the same backend. And this is a typical use case for having some kind of interface description. And once you have an interface description with a machine-readable format, you can generate all kinds of code from this, and that basically solves this problem of having multiple API endpoints or other output. In Rust, what you see a lot for FFI or RPC frameworks is that you define your trait, and this actually gives you your interface. You put some macro derive on top of it. And that actually parses your trait and then generates this specification from that. For us, that didn't work as nicely or as smoothly because we also wanted to support properties. That's not something that maps very trivially to Python to Rust traits, and also some other stuff. So we didn't use this route from we didn't use the derive macros per se, but we actually started one point later. So we defined the API definition as part of our struct thing. So you have this property struct, for instance, which has the doc string as a property or the physical unit, which you might specify, which is of course very important for us. And then once you have this filled with data, you can use that to generate all kinds of code from this. So this is just normal code generation. So for instance, one point back. And the nice thing here, why I think this is also a strong point for us, is that then writing your interface description, you can do in any language that is compatible with SERDI by just adding these serialized and deserialized derives on top of your trait. So we actually do specify our API using some kind of JSON, so JSON 5, so it's a little bit more easier to write by hand. But we actually do write these kind of files by hand. They're relatively simple, and feed them into our Rust toolchain, and then they generate a bunch of code. In our case, we do actually generate traits from this. So in order to implement this on our controller, we get this looks a little bit you can probably not see everything immediately, but this is essentially the interface that I showed you before, and this is something that you then need to implement on your controller. So the properties, for instance, always map to getters and setters. So this is more or less trivial stuff in terms of code generation. We also generate the binding the glue code from the service library endpoints to these traits. So calling into these traits is all generated automatically. Also some Rust client code for testing purposes mostly. But we also generate the SCPI command set and the documentation that we want to put in the manual from the specification. And furthermore, also the code, as I mentioned in the beginning, used for the user interface. So the user interface itself is not automatically generated. We do that by hand because it should look nice. But the library that the TypeScript app uses that maps over our API is generated automatically, as is the case also for the Python stuff. So this is all what we get out from this specification. Then going back to the system, we also have microcontrollers, as I mentioned in the beginning. So one of the systems here on the right may look like this. This is the driver electronics for our measurement chips, actually, for our sensor chips. In our case, this runs on STM32, as I mentioned in the beginning. And there's good support for this. So no vendor support, but there's good community support from, for instance, from the Embassy STM32 crate, which is very nice and well maintained. And offers essentially support for huge bunch of different STM chips. And note, by the way, they also made use a lot of code generation to generate the code for the support code for the different STM chips, for instance. So that's also a use case where code generation is used heavily. But again, then you still have the thing that you need to communicate between this box and the main control unit. For this, we use as a protocol, so some kind of standard protocols. We use the CAN bus, which has nice electrical properties also and can be shielded well. We use a slightly customized protocols on top of some standard protocols. But again, you have some interfaces, and this kind of sounds familiar because it's the same story that we have before, and we do a lot of code generation again. So we specify the API with the same logic as we did before for the other side of the interface. just for the part between our main control unit and the microcontroller. So in this case, you get out a bunch of traits that you now implement on your microcontroller, and essentially it's the same code that you use for both the computing platform and the microcontroller. You auto-generate some client libraries that you then use from the other side, from the main control unit. And also in this case, we generate Python APIs automatically because our electrical engineers want to test this box by themselves on their own. They want to hook it up to a PC without the rest of the system being present. So it's nice to having, for calibration and so on, a Python API available. And then in this case, we do have also an auto-generated graphical user interface, which is just nice because it lets them, toggle some LED or switches with the press of a button. Now so how much time do I have left? Like 10 minutes, okay. So to go a little bit deeper, when you are on this embedded part, at some point you run into the problem that some of your chips that you want to target don't have Rust drivers available, but somehow you need to talk to them. So the typical case on how you tackle that is, of course, you look at the data sheet, you look at the commands that they provide. In this case, this is an analog to digital converter. So it converts some voltages into digital values. And this is served using a protocol which is rather low level, which is called SPI. And to write, so either you're lucky and there's a crate available for this already, or you write it yourself, which is not super difficult to do. And well, how do you actually go ahead and do this? Well, essentially you start with a simple struct, and then you just add the impulse on the struct as you would implement any kind of API. But in this case, you want your driver crate to be usable in no-stat environments like your microcontroller, and also maybe for testing purposes hooked up directly to the compute module or other parts. So you're being generic over the actual SPI bus that you get, and the traits here, in this case the SPI device traits, they're actually in this case provided by the embedded HAL crate. So this is fairly standardized in the Rust ecosystem now. And typically, the very least that you do is you expose a lot of registers, basically all of the registers that the chip offers you. So there's also, I think, a talk later today that covers on how to automate this, also using code generation. But then often it also makes sense to maybe provide some higher level functionality, because for the example of this analog to digital converter, for instance, you need to interpret the data that you get back in the end in a certain way, or you need to do some logic around this. So the actual communication is only one part of that, but you might have some more code around that. So that you put all in your driver crate. And then once you're finished, you can nicely integrate that into your system, either on the microcontroller, where you include this as a crate, and typically the code base is then not very big, or on the compute module or on your PC. Regarding this, I want to mention, I go quickly into the sync versus async topic a little bit, because there's two observations that I made, or that we made here in this case. So first of all, for this example, here we use this chip uses, as I said, an SPI protocol. And interestingly, SPI, for those of you that have used it before, actually is more or less a synchronous protocol. So it's a real-time communication, right? So in this case, for instance, you write 8 bits, and by the time you wrote the first 2 bits, the device or the chip already decides what it will send out on this output line. So essentially, after writing this 8 bits with your fixed clock rate, you will have the 6 answer bits in your input buffer already, right? So it's very synchronous. It's a real-time operation, essentially. The clock rate is fixed. So you could argue it's a synchronous interface, but then, of course, on the higher level, you always still have some asynchronous operations. For instance, for the analog to digital conversion, this may actually take some time. So not the communication itself, not getting the response, but actually doing the measurement on the chip takes some time. The sampling, maybe some conditions need to be met. And typically, the chip then signals this over another channel, like, for instance, by raising an interrupt pin or something, or you actually need to poll the register, which changes its state if you don't have an interrupt available. So on a higher level, you are async again. So that's just, I think, an interesting observation, because you always need to decide whether, or keep in mind, is something synchronous or asynchronously. And the second thing or second aspect that comes up when you implement such a driver is that you always, you have to decide, are your methods that you implement synchronous or are they asynchronous? And right now, the way, so embedded HAL, I think there's a separate crate for the async traits, but you have both of these traits. So you have one trait, SPI device, in the async and one in the sync case. And to allow both use cases, you actually have to implement it twice. And this is not a very nice user experience, I would argue. In our case, we implement them mostly unfortunately, mostly synchronously, and then in our use case, we actually wrap them as a blocking call to run on a separate thread pool or whatever. Because otherwise, you really have the double effort. And I mean, there are some efforts underway to be generic over sync versus async. I haven't really followed that lately, but I think, this is also, I guess, a difficult topic to tackle. Another thing that could help here would also be code generation, and I think maybe the talk later today will cover that. So I think that's just really one of the rough edges that we encountered when implementing these device drivers. And so finally, let me come to the slide that I showed in the beginning before. These points all hold. And as a conclusion, I'm really happy that we did choose Rust in the end. However, in order to not only preach to the choir here, and to be completely fair, let me also put the second half of the slide that maybe belongs here, because maybe you also, when you have such a choice, you also need to be aware of the challenges that come with this choice for Rust. And the first thing is that, the ecosystem still does have some rough edges. I mean, that's probably true for every ecosystem, but you need to be aware of them. So, for instance, the async traits, not all of them are standardized yet. If you want to switch between runtimes, that's old topic. That's still not part of the standard library yet. And also this sync and async duality that I mentioned, I think is still a point that could use some love or could use some work. But maybe the even bigger point is that in the embedded use case, there's often no official support from the vendor for us, for your target platform. I mean, this is slowly changing now. There's a booth from Espressif downstairs, I think. So there are examples where this is changing now. But on a broad perspective, this is still more the exception than the rule that you have official vendor support for Rust. And of course, if you're a company that also has to provide support, that actually matters a lot to you, because you may want to have support, like commercial support being available to you. And finally, this is probably the biggest point for us is, yes, it's still difficult to hire for this kind of engineering positions, because I'm not only talking about just Rust engineers. I think there are many Rust engineers now, which is good. And by the way, we are actively hiring. So if you're interested in working on such a field, please always also come talk to me. But we're also like people with mixed backgrounds. Like we have a lot of physicists working in our team. We have electrical engineers, and typically they don't get exposed to Rust as part of their education. They get exposed to, Python in the case of physicists or C in the case of electrical engineers. And they always then ask the question, so, okay, why did you use Rust? I've never seen this before, and so on. So, it's difficult enough to hire an electrical engineer by its own, but to hire one that also knows Rust or has had some experience with Rust is, for a company like us, it's like almost impossible. So this is something that you need to be aware of. It didn't scare us really, and I think in that sense, I think the title of the talk is somewhat fitting, because yes, Rust offers you this fearless concurrency and other features, but of course you also have to be a little bit fearless to, at this point, in a small company like ours, also employ Rust and choose it as your tool chain of choice, essentially. Yeah, and with this, I think I'm at the end of the talk, and I'm also around for questions. So happy to answer any questions that you may have.
I think we have some time for Q&A. This mic not there. Do you have some time for Q&A? Yeah.
Hi, I have a couple of questions. So you mentioned between the microcontrollers and the main control unit, it's a CAN bus, and then from the main control unit to like the API or the host PC that they're running their applications on. Is there like, what implementation of SERDE are you using? Is there like Postcard or CBOR or something like that?
Yeah, for the WebSocket part on the left side, we use SERDE JSON, I think. JSON SERDE. I don't know which way around, but this one. And for the other, I think we use Postcard actually in the backend for the serialization between the microcontroller, which
And then my other question was, you should like device RPC. Is that a crate you made internally, and is that open, or is that?
It's a crate that we made internally, and we plan to open source at some point because it contains, I think, a lot of cool stuff that we built. So I just reserved the crate name because it's the first time that we show this publicly. It will be open source at some point. We're just still in the process of doing that. It will take a few more weeks or so, but yeah, we definitely plan on open sourcing that.
Cool.
Also, a lot of the driver crates will be open sourced soon. Yeah.
Thank you.
Yep.
I've been doing quite a lot of driver development recently as well. I was wondering if you had heard of the maybe async crate, because that's quite nice. You can write async, well, your API in as async, and then convert it to synchronous as required.
Yeah, so we also utilize that at some point or utilize that at some part of the toolchain. It's just, I think the rough edge then is that it's not part of the of the official packet or the official solution. So you have to know the crate, you have to use it then. And I think, as I said, I didn't really follow the debate anymore about making it stuff generic over sync or over async, but that would be a solution that is really embedded into the language, and that would make things a lot more straightforward. But of course, there is support. This is one option. The other would be just to use also other kinds of code generation, which is essentially working the same way, I guess. Yeah. But it's a good hint. Yes, maybe async.
Hey, thanks for the talk. I was wondering, in your opinion, you mentioned one of the gaps being about lack of official vendor support.
Mm-hmm.
What do you think vendors can do best to kind of mitigate that, given that they have limited resources as well? Is it just PAC support? Is it full embassy? What would you recommend to the vendors?
So you mean like STM and so on? Yeah. I think the most important thing really is, in our case, we're a small team, so we get to make a lot of decisions in ourselves, and there's not management or a certification that prevents us from making some decisions. But I think in many cases, it's already just valuable if you have some form of, or can claim some form of official support, because then your engineers can point to management that, okay, this is not a business risk to decide for this language, because even the vendor supports this. So this is, I would say, the baseline. But then having tools. I think for STM there's a lot of tools. I haven't really used them myself a lot, but the electrical engineers use them to generate a lot of C code, and they just click and configure the system in a way that they want, and then they get C code out of that. So there's a whole ecosystem behind that, which all targets C. And I think there, if you had a few more tools available that also offer Rust as an option, that would be nice. And finally, I guess documentation, obviously, and maybe examples to get started. And I think in the long run, it's really, you probably really have to get into the universities or the schools that actually train the electrical engineers, and that they get in contact with Rust at this point, because if they never get exposed to Rust, they will always only ever see C as part of their education. Then at least the learning curve will be a lot steeper when they actually encounter something like Rust being used at their job at some point. So I think the education part is also, I don't know how the connections are made between the vendors, but I guess there's a lot of cooperations there, and I think that's a good opportunity also to enter the market with through the education part. Yeah.
Thank you.
Yeah, you're welcome.